Hello everyone, welcome to our YouTube channel. I am Aparna MK, finally at Triply. Today we are going to learn V by F control of induction motor, which is the most common method in industry to control the speed of induction motors. Here we will maintain the flex and torque by maintaining the V by F ratio as constant. Now we are going to discuss how to maintain V by F ratio as constant. If we increases the frequency, then we need to increase the voltage as well to keep the V by F ratio as a constant. As well as if we decrease the frequency, we have to decrease the voltage in order to maintain a constant V by F ratio. Constant V by F ratio maintain the torque and flux as constant. Next, we are going to learn how the frequency of induction motor changes. It completely depends on the desired rotor speed, that is N star, at which speed we want to rotate the induction motor. Based on that, the line frequency to the induction motor has to be changed, by which the synchronous speed Ns changes and hence the actual rotor speed N. Next, we are going to discuss an important point, that is how to change the voltage of induction motor with respect to frequency. As we already discussed, if frequency increases or decreases, the voltage has to be increased or decreased as well. So if we draw a graph between frequency and voltage, it will be almost linear. There is a important point that we have to be noted in this graph. The first important point is there is a need of small voltage boosting to be applied in low frequencies so that E will be approximately equal to V. It can be interpreted in another way. It is to compensate the voltage drop in stator winding resistance R1. To understand it in a better manner, we can consider this per phase equivalent circuit of induction motor. To make the equation 1 as valid equation, the terminal voltage V1 need to be approximately equal to the equation EMF E. That is, the voltage drop in resistance R1 and reactance X1 should be small. Generally, reactance X1 will be very small when compared to the mutual inductance Xm, and hence it may neglected from consideration. However, at the low frequency, the stator terminal voltage V1 is comparable to the stator resistance drop in R1. To compensate for the stator resistance, we need to apply a small voltage boost at low frequencies. Usually, voltage applied to 1 M should not increases beyond the rated voltage to carry out insulation breakdown in stator winding. So beyond the rated voltage or base frequency, the voltage will be maintained constant. So we will not be able to maintain the V by F ratio as constant, and hence the maximum available torque decreases in this region with increase in frequency. We don't have any other way to maintain the ratio as constant. So whenever we are operating beyond the rated voltage, we need to sacrifice the maximum available torque to avoid the insulation breakdown in stator winding. Next, we are going to see the torque speed characteristics of V by F control. As you can see, when voltage and frequencies varies along with a small voltage boosting of low frequencies, then the maximum available torque is constant. Hence, it is called constant torque region. Along with a constant torque, we can get very wide speed variation for the given load torque. Additionally, you can get high efficiency since the slip proportional to ns minus n, which is low even if it is in low speed, that is ns1 minus n1, or in high speed ns5 minus n1. But beyond the rated voltage or base frequency, the voltage has to be maintained constant. So, the only parameter we can vary beyond the rated voltage is frequency. So in torque speed characteristics, maximum available torque will decreases as you can see in this picture, and there will be no stiffness in this torque. So slip proportional to ns minus n will be high, and hence the efficiency will be less. Since the torque and flux are decreasing beyond the rated voltage or base frequency, the region is called flux weakening region. Usually, we will operate induction motor in this region when speed is the only desire for the motor. Now, let's see the implementation of closed loop V by F control using PWM method, which means it will have 3 sinusoidal signals and 1 triangular signal as shown here. Closed loop system is used where precise speed control is required, because even if any external disturbances happen, the closed loop system identifies its and maintain desired rotor speed n star which we want. So the first step is to sense the actual rotor speed n using speed sensor. The desired rotor speed n star can be given by any non-technical person. Both n star and n is compared in this error generator and generate the error which is equal to n star minus n. This error will be given to the controller, and the job of the PI controller is to change its output until the input error is 0. So the output of the PI controller is the desired slip frequency. In induction motor, torque is proportional to slip speed ns minus n, and hence the slip frequency fs minus fn, or simply f minus fn. That's why this PI speed controller in induction motor is considered as slip frequency f minus fn. Next, the slip frequency has to be neglected using slip regulator so that it will resist the operation below the breakdown frequency at which the maximum torque develop in the induction motor. Now, the slip frequency f minus fn is going to be added with rotor speed frequency fn, which can be get in we multiply the rotor speed with p by 120. So we will get the desired frequency f star. Because f minus fn phase fn will be equal to f, which is stator frequency or line frequency. First, with the desired frequency f star, we can get desired voltage v star using look. Include the characteristics as shown. Next, the desired frequency f star is converted to omega star by multiplying it with 2 pi. Then omega star to omega plus star by doing integration. With this desired voltage v star and even omega t star, we can able to get 3 sinusoidal signals for PWM control circuit. To avoid confusion, first convert that into 2 sinusoidal signals, V alpha and V beta, which we have 90-degree phase shift. Then the desired two-phase V alpha star and V beta star are converted into 3-phase VA star, VB star and VC star using inverse clock transformation. Finally, the desired 3-phase VA star, VB star and VC star will be given to the PWM control circuit, where it will be compared with the triangular carrier signals and generate the gate signals. For switches in this inverter, at last the inverter will give the desired voltage and frequency based on the desired rotor speed given. Here, both the voltage and frequency is being changed into the rated voltage. So the maximum available torque will be maintained and efficiency also be high. As I have mentioned earlier, it is the most common method used in industries to control the speed of induction motor. Thank you so much for watching this video.